Hello, my name is Brentley Robertson, and my project is an EKG machine. This project sets out to solve the problem of having a cheap EKG machine that can view and record heart signals and, most importantly, be able to visually identify the PQRST, which we'll see later. Um, Using an operational amplifier, we can isolate the heart signals, and we also are using cheap disposable EKG electrodes. These actually came from a fire department. Uh, Processing the heart signal data involved a low pass filter, which was basically used to just remove a lot of signal noise that was closer to the baseline voltage that we had, which we'll see later. Um, Things like recording and interpreting the heart signal data, that was just writing to a file and opening it in Excel. Now for the electrodes, they use this conductive wet gel, and they have a silver or silver chloride uh, sensor, which I guess is that little metal piece, if you can see, within the blue dot in the center of it. So my first design of the circuit relied on this common mode noise cancellation. So as long as this noise was present in both inputs, the goal was to remove that completely. So then it would allow me to have different parts of the body providing an input, and then isolate something. This didn't work out at all, really. Um, but here's another image of the emitters being tied together. You can see here this emitter and that emitter. They're both on the same row. So these capacitor negative ends were used as signal inputs, and at first I was just touching it with my fingers, which we'll see in the next slide here. That really I started just taking oils from my face and touching these negative signal inputs on these capacitors to get some sort of signal output. And right here you see this is one finger on one of the ends, but the other one is untouched. And then I take this one finger off and I touch the other one, and you can see it just jumps up quickly and down. And over here is where I touch both of them. And what I found to be interesting here is that uh, it actually was just making these surviving waves more clear. Instead of isolating some signal like the heart or something like that, it was just making this 60 hertz. I think this was like it's on the next slide. Yeah, it's an aliased signal that was surviving. So uh, because we were sampling at such a low rate, we'll see later that it was 60 times per second, right? Um, there was a surviving wave left over from the 60 hertz signal, and this right here just explains what the common mode gain is supposed to do, where you see this really noisy sinusoidal wave, and then gradually it's getting more and more clear, more and more perfect. But so it did remove noise from the signal, but what it did not do was read the heart signal or isolate it. So this is the final design of the circuit, and here I'm using an LM324. It's just an operational amplifier, and then the 7660 is a voltage converter. So I was able to take a 9-volt battery with that and have 9 volts positive and then negative 9 volts. So there was an 18-volt potential difference when using this integrated circuit. And the last part of the circuit was this voltage divider that I set up. It's on the right side of the board, but you really can't tell what it is because it just looks like these capacitors with really long legs. And yeah. So for the 7660, the important thing here is that we're getting the positive 9 volts and the negative 9 volts, this pin 8 and pin 5. That's the whole point of it, really. And that's used to power the op amp here. Right, we can see VCC on pin 4 to 9 volts and VEE to pin 11 to the negative 9 volts. So this is where where we actually have input going on, and this is chest electrode 1 on pin 3. Pin 3 was right here, or right here if you're looking at the IC view. And then pin 5 we had another chest electrode. But there was also a chest electrode that was attached to ground, and it's uninvolved with this integrated circuit due to the fact that that's simply something that connects to the entire circuit's common ground, right? So the output here was actually going to a 1.65 volt bias divider that we discussed earlier. And the reason for that we'll see on the next slide, where due to the fact that the analog to digital on the microcontroller was not able to read under 0 volts, a negative voltage, anything outside of the range of 0 to 3.33 is not going to be read. So what I had to do was set up a bias so that it would be like a mid-range value where we're starting from. So as the heart signal goes up and goes down, it'll vary and it'll push it up, but not to a value that's above 3.33 and not below a value like 0. We'll see in the end that it stuck pretty close to 1.6. I don't think it ever really went above 2 volts. So yeah, this was basically two identical resistors. One was hooked up to the 3v3 from the microcontroller, so positive 3 volts, and then another one was hooked up to ground. And what this did is that it just split the voltage in half, so I could use that as a baseline voltage. So here are the electrode placements, and really it wasn't quite like this, where these are much more close to the clavicle, closer to the shoulders and so on. Really, the way I had it, this RA was really just right over my right chest section, and then the LA was right over my heart, pretty much on the left. But this LL, I kept that on my lower left rib. So, yeah, this pin 3 and pin 5 input, we'll see that it was kind of interchangeable, and we'll see why in a second. But I think the ground is the most important piece, actually, and what really made the circuit work, because I think that was draining a lot of excess AC signal in my body. So for the code, we started off with something really simple at first. This is vtrack.py, and right here it actually just prints out to the console. So I was using Thonny, which is a MicroPython or Python writing tool, and basically we see here that we're printing out the voltage, converting it after we listen to this pin 26, and I was copying it over to Excel and graphing it for a little bit, but later on we had this code, and this was a bit nicer. It's much faster at 250 hertz. Previously it was every 60th of a second, right? So now it's 250 times a second. So the resolution should be a bit better when we're actually recording the heart signals. But the most important thing about this was that it was actually writing a file and writing it to the microcontroller's memory itself. With the last code iteration, I had to just copy it from the terminal, and the terminal had a limit. After a while, it would just start moving the screen down. It can only have so many lines on it at a time. And then for the third iteration, this is where we included an exponential moving average. And so this was used to smooth out some of the noise that appeared between the heartbeats. And I think I show an example of it, but basically this was really important due to the fact that really close to the baseline voltage there was always a lot of noise going on. So using this, I was able to smooth it into something that was much more realistic looking, actually. So this is an example of the kind of effect it can have on the noise and how it can end up making a bunch of noise look like a nice sinusoidal wave. So it's uniformly applied, but it does also lower the amplitude of the entire heartbeat cycle. I found that out. When I compared it with the unfiltered data and the filtered data, there was always a reduction in the amplitude. So really, I would say this isn't completely accurate as an example. So these are some of the results. You can see it sticks pretty close around 1.65 volts. Here, like 1.66, where it's kind of an average. But um, so they were successfully isolated using this circuit, but the data was recorded upside down, and we can see that because the initial spike in voltage here is negative. So here it is running, and it goes negative, then to positive, and then there's the T wave. But so what we did to solve this is that this possible method of fixing the inversion issue is how the electrodes were placed. And so if we just switched pin 3 and pin 5, it flipped it back over. And here's an example of that. This is real data taken from my heart. But there's a lot of noise going on after this initial spike in the heartbeat. This should be a much more clear T wave in this highlighted section. Instead, it's like really jagged, really ugly looking. So what I ended up doing is I just inverted the data that I had. And really, I gave it a lot of trial. So I'm completely unsure still why exactly I was unable to get just the opposite pin ordering to make to make data that was more clear, more presentable. But what this ended up doing is that, hey, that's realistic. That is really a clear indication of the heartbeat signal and the cycle thereof. So these are some of my best results, and you can see that we have all these regions completely identifiable. Here's the P region, Q region, this slight dip, and then here's the peak, the R, the S, and the T. And thank you very much. This is a 3D printed container I made for it. It actually fits around the ridges of the breadboard. There's a lid for it, and then also I created room for the alligator clips so that they could stick inside of it but still be rigidly held, and then there are the electrodes attached. So thank you very much.